In this video, I will cover the rules for naming and writing covalent compounds, the way we will use them in chemistry class this year. I think you will find this much easier than dealing with ionic compounds. Remember that covalent compounds contain only nonmetals, so there's just fewer elements to choose from because it's just that upper right corner of your periodic table, like I have excerpted here, plus hydrogen. In covalent compounds, electrons are shared between two atoms instead of being transferred completely like they are with ionic. So you don't have ions. They do not form any ions, but the molecule itself might be slightly charged. And that's something known as polarity, and that will be something that we're going to cover in much greater detail later on in this course. Covalent compounds also can be known as molecular compounds. This is because they really do form true molecules, whereas ionic compounds form crystal lattices. So it's a little bit different in kind of the structure in a way that we're really not going to talk about much. But that's another name you need to know, that molecular compounds and covalent compounds are the same thing. So naming covalent compounds, you have the first nonmetal name with like you would have just for your ionic compounds, you're using the full element name. And then you have the nonmetal ion name, the anion name that ends in "ide," just like you had with ionic compounds. But the name themselves includes prefixes that will tell you how many atoms of each particular element are in the compound. So unlike ionic compounds, which don't give you any indication in the name how many atoms there are present, the covalent compound naming system tells you how many of each is there. So you need to have a sense of what these prefixes mean. Mono means 1, di is 2, tri is 3, tetra is 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. So you need to be familiar with these prefixes. I will include them on the quiz, so you'll have that list there, but you've seen some of these, I'm sure, in geometry. Some of them are the same as the various shapes, and some of the other ones are new to you. Here are some examples of covalent compound names. If there's only one of the first element, you don't need to use a prefix, so they're not going to start with mono anything. And if the number prefix itself ends in an A or an O, which most of them do, and the element starts with a vowel, often the prefix vowel is dropped. This is especially true if it's an A or an O. I's tend to stick around. So this first formula, S2O3, has a name of disulfur trioxide. So di is the prefix telling me there's 2 sulfur, and tri tells me there's 3 oxygen, and because oxygen is the element is in the second place, it becomes oxide. So everything's going to end in "ide" when you're dealing with covalent compounds. CCl4 is carbon tetrachloride. So tetra meaning that there are 4 chloride ions there, or 4 chloride atoms, sorry. They're not really true ions, so 4 chloride atoms. P3N5 is triphosphorus pentanitride. So again, your prefixes are telling you exactly what is there. You've got a nice relationship between the name and the formula. Carbon monoxide, notice we are starting off without, it doesn't say monocarbon, it just says carbon. We don't put mono if it's the very first element. And then since mono and oxide are both, the mono is ending in O and oxide is starting with O, we just put only one O in the middle and it becomes monoxide, not monooxide. And then I3, nitrogen, and then triiodide. So as I said, usually the A's and the O's go away, but the I's always stick around, even in this case where we end up with 2 I's on top of each other. So since you already know that the prefixes tell you how many of each atom is present in the compound, if you're going from a formula to a name, then going from a name to a formula is very, very simple because you just use the prefixes to go the other way. So if we have tetraphosphorus decoxide, then you know the tetra refers to 4, so there's 4 phosphorus, and then the dec was deca, but it ended in an A, so the A went away to become next to the O for oxide. So decoxide, so we have P4O10. So again, just use the formulas to tell you the prefixes to tell you how many atoms there are of each. Disulfur, dibromide, you've got 2 of each, S2Br2, and then silicon dioxide, 1 silicon and 2 oxygen. So this is very, very simple and straightforward, and quite a relief from all of the adding of charges and the balancing that goes into making ionic compound formulas work out. We have a couple other naming systems that are involved with covalent compounds. We have certain covalent compounds that we use common names instead of their formula. So we just talk about H2O as water. We don't call it dihydrogen monoxide. NH3 is ammonia. And again, we don't give you the nitrogen trihydride. And CH4 is methane, not carbon tetrahydride usually. Organic compounds, compounds that are built around carbon and found in living organisms and can be quite large, have an entirely different naming system based on the molecular structure of those different molecules and the functional groups that can be identified. We did a tiny bit with functional groups when we were talking about our biological molecules in biology. I don't know how well you remember the carboxyl group or the amine group. And so in these organic compounds, you get crazy names like this one down here that I'm not even going to try to say. But to someone who works in organic chemistry, they can draw the molecule exactly, and this is a fairly large molecule, but they know exactly what it looks like based on this rather long and intensive naming system. So what you need to know about naming covalent compounds is to know how to use those prefixes to identify how many of each atom are in the formula, and then just to go back and forth between formulas to names and names to formulas. Very easy, much simpler than what we did with ionic compounds. I don't think you'll have any trouble with this.